We're going to take one more approach with the gravity analog. So several reasons we do this, but two of them, or three of them. One, it's fun. Two, it shows how different physics equations actually work for totally different physical phenomena. And three, we understand gravity. We can see that. Electric potential is a little trickier, so by showing how it kind of fits in with gravity, at least mathematically, hopefully it'll make it a little easier to understand. So we're going to consider a mass on an inclined plane. The slope of this plane determines the acceleration and the net force on the object. For example, if it's sloped like this, there's no net force and it's not going to move. If it's sloped at more of an angle, it will accelerate. There's a greater force on it. So here the net force is 0. Here the net force is equal to something related to gravity. A similar relationship exists with uniform electric fields and voltage. With the inclined plane, a difference in height from the bottom to the top was responsible for acceleration. Here, a difference in electric potential or voltage is responsible for the acceleration. Let's see if we can relate these facts by placing a positive charge in the below field and using this equation. Let's start with the mass on the inclined plane and use the conservation of energy. This E is not electric field, it's energy. So the work-energy equation shows initial energy plus work equals final energy. We'll assume that there's no friction in this problem, so there's no external forces, so work equals to 0. The energy at the top of the incline is mg delta h, and at the bottom all of it is converted into kinetic energy, so that's 1/2 mvf squared. Since we have a constant acceleration, we can use one of the kinematics equations. We'll use a third one. Vf final squared equals the initial velocity squared plus 2 acceleration of the mass times delta x. Now we're starting at rest, so v0 equals 0. Our final velocity will be 2am delta x. We substitute that in right here for this term. We notice that we have m's that can cancel out. We notice that this 1/2 cancels the 2, and we wind up with g delta h is the acceleration of the mass times delta x, where delta x is the distance it's sliding down the incline, h is the height of the incline, and we come up with the acceleration of the mass is g times the change in height divided by the change in distance sliding down the incline. So if we have the incline like this, this is your x term and this is your h. Now let's switch over to the electric field between two planes. We start again with conservation of energy, and we have the charge up here at the top. This time there will be no external work on the charge plane system. This charge will accelerate and increase its velocity as it falls down in the field. So the work is 0. So my initial energy is qv0 equals qvf plus 1/2 mv final squared. My next step is to take qvf, put it on the left side of the equation. So I have qv0 minus qvf. And now I'm just going to reverse these and put a negative sign here. So basically I've just put this guy in front of the v0 and factored out the q. So I have this expression here, which we will bring to the next page and see where that leads us. This is the equation from the previous slide, and now you're going to see the reason why we took the q out and why we switched the order. Vf minus V0, final voltage minus initial voltage, is nothing more than delta V. So I now have minus Q delta V equals 1/2 mvf squared, and just like we did for the inclined plane, we're going to use kinematics. Whether a charge is moving or a mass or a block, kinematics still works. The charge started with an initial velocity. We use the third kinematics equation to show that its final velocity squared will be 2 times the acceleration of the charge times delta x, which is how far it falls in the field. I replace Vf squared with this term here, And now I'm left with this equation, which I will now bring to the next page. Here's where we were on the last slide. I will cancel the 2's, and I have minus q delta v is equal to m times the acceleration of the charge times delta x. Recognize ma? Of course, that's the force. And in this case, it's the force due to the electric field. Inside a parallel plane, or actually anywhere, the force on a charge is equal to q times the electric field. Within the parallel planes, we're fortunate in that E is constant. So we are going to replace this MAQ with QE, right? MAQ equals F equals QE. I now have Q's on both sides. I cancel the Q's, and I come up with the equation that we derived in a different fashion, where the electric field is negative delta V over delta X. So what this is telling us, the electric field is a measure of how the voltage changes over a displacement in space. The negative sign tells us that the electric field vectors will point in the direction of decreasing voltage or from positive to negative voltage, which is also decreasing voltage. Let's look at what we've derived here. We found out that the acceleration of this mass going down the incline is equal to g times delta h, all right, this is your h over here, divided by delta x, where x is measured along the incline. We've also found out that the electric field is equal to the change in potential over change in x, the negative of that, and x is measured in this direction. How can we compare these results to show how the gravitational field is analogous to the electric field? We want to compare the acceleration of a mass sliding down an incline, and the incline kind of represents the electric field, to the acceleration of a charge moving in an electric field. We already have the acceleration of the mass. Now we want to find the acceleration of the charge. We will use force equals QE. We know that E is minus delta V over delta X, so we're left with the force is MQ times AQ. We divide out MQ, and we're just dealing right over here with these two guys, and we come up with the acceleration of the charge in this uniform electric field is minus Q over the mass of the charge times delta V over delta X. Here's what we've been aiming for. We have found out that the acceleration of the mass, it will depend on g. The greater g is, the greater it accelerates. And you've got this term here, this delta h over delta x. Delta x is along the incline, and delta h is up here. So for a given height, the smaller x gets, that means you're coming in closer like this, that would be a smaller value of x than here, your acceleration will be greater. That makes sense, it's much steeper. As x gets longer, you have much smaller acceleration. For the case over here with the charged particle in the parallel planes, the greater the charge, the greater the acceleration. The greater the mass, the smaller the acceleration. And the greater change in voltage over a distance will give you a greater acceleration.